Hi, today we are reviewing 4.3 right triangle trigonometry. So this is straight from geometry. And then we're also going to look at some applications. So you'll find the applications in 4.8. I will do those on a separate video so you don't have to listen to both videos there. Now, the first part of our lesson, we're going to go over some properties that you need to know, that you need to start working and committing to memory. So that's going to be this group. We'll talk through those. And then we're going to work through these problems down here. Okay, so you got to really get yourself together and start thinking about identities. When we get into trig, we'll actually have a full page full of trig identities that are going to be more involved than what you're seeing here. So it kind of looks like this, and we'll go all the way through. So this is going to take us through all of chapter 4, which is basic trigonometry. So that's basic trigonometry skills, and then basic trigonometry graph knowledge. And then we'll do chapter 5, which is applying an analytical type trig, where we're going to actually be solving for equations, be looking at proving trig identities and some things like that. Then we'll move into chapter 6, where we'll pick up some other trig topics where we're using law of sines, law of cosines. We'll be talking about parametric and polar equations, so that kind of stuff. So let's start with the basics. So let's get right to business here. One thing I want to make sure as we start this is make sure you understand the notation. When you see sine squared theta, it equals sine theta squared. So what this means, remember, is sine theta times sine theta, and so that is how you have to enter it in the calculator. Theta represents an angle. We'll use theta, beta, gamma, alpha, all kinds of Greek letters. You'll get accustomed to that as we go through this process. But just remember that's the part that's representing the angle. So in geometry, right triangle geometry class, you learned about the triangle with a right angle in it. We marked our theta angle. Then the angle that's opposite on the other side of the angle is what we call the opposite side. The one that's adjacent or stuck to it is the bottom one here in this case, because theta is right here. And the hypotenuse is always the longest side in the triangle, always opposite the biggest angle, which would be your 90 degrees. You also learned about SOHCAHTOA, which gives you the first 3 basic trig ratios, and the 3 letters represent the ratio of the sides. So this is an angle that has a sine ratio of opposite over hypotenuse. So cosine of theta is adjacent over hypotenuse, and tangent of theta is opposite over adjacent, and that's what these letters mean right here. So I know nowadays we learned SOHCAHTOA. Back in the day when I was doing it, my teacher had me write an equation that was an acronym. So my equation was, so how can April help Trevin on algebra? Which was good for me because Trevin was my brother, so it made sense. So if SOHCAHTOA doesn't work for you, be creative, come up with an acronym, but I think SOHCAHTOA is great. It's short, sweet, to the point. So then those are the ratios from SOHCAHTOA. There are actually 6 trig functions in total. We have sine, which we learned, and cosine and tangent from our SOHCAHTOA. But then we have cosecant, secant, and cotan. So when we're doing the reciprocals, a reciprocal just turns the fraction upside down, right? So cosecant goes with sine, and I turn the fraction upside down, the ratio, so now it's hypotenuse over opposite. And then secant goes with cosecant, so that's hypotenuse over adjacent, and cotangent goes with tangent, that's adjacent over hypotenuse. So whenever I'm actually finding all 6 trig ratios, I definitely pair them up. So everybody can remember that tan of theta and cotan of theta go together. That's pretty easy. So how do we know, does cosecant attach with sine or does cosecant attach with cosine? So the way I remember that, and you're more than welcome to use what I do. If it doesn't make sense to you, feel free to lose it and not use it. You will not hurt my feelings. But I was always taught that every co has a non-co. So the prefix on sine is sine, no co-term at the beginning. So that has to pair up with the cosecant term because that co-prefix is down here. When I look at cosine, co is up here, so that means it attaches with the secant. And that's how I remember how these two go together. The next set of identities are the actual reciprocal identities. So these are ratios, and these ratios are reciprocals to each other. But we actually have reciprocal identities, and that means 1 over the function. So as we learn reciprocal identities, we know that also means 1 over. So a sine of theta is 1 over cosecant of theta, because remember this was a reciprocal, so it's 1 over that reciprocal. So I could say sine is opposite over hypotenuse, or I could say sine is also 1 over cosecant theta. Then we have cosine, which is 1 over secant theta, and we have tangent, which is 1 over cotan. Now you can just remember this list right here and understand how this connection moves around. So if I wanted to find cosecant, that's the same thing as 1 over sine. So if you prefer to have your 6 reciprocals written out, that's fine. But you can also generate them from here because I know cosine of theta is 1 over secant, but now I know secant is 1 over cosine, excuse me. So then if I want to know tangent, I know tangent is 1 over cotan, but if I want to know cotan, all I have to do is go 1 over tan. So it's up to you which way you want to learn them. Either works equally well, but these are things that will need to be committed to memory, so come up with a good strategy there. The next group of identities is the quotient identities, and so I have tangent of theta equals sine over cosine, and cotan of theta equals cosine over sine. Quotient means division, and so we're writing the ratio as a fraction because that's also division. So if you want to look at all of the things we know about tan, we know tangent is opposite over adjacent. We know tangent can also be 1 over cotan, and we know tangent can also be sine over cosine. So all of these things are kind of connected together. And then we know that cotan can be adjacent over opposite. We know cotan can be 1 over tan of theta. And so since cotan is the reciprocal of tangent, we know it can also turn this fraction upside down and be cosine of theta over sine of theta. The next group of identities is Pythagorean identities, and the Pythagorean identities are the first time we've talked about anything that has a power of 2, so it's higher than a power of 1. Think about the Pythagorean theorem, which is a squared plus b squared equals c squared. All of those are powers of 2. The Pythagorean identities are all powers of 2 as well. So we have sine squared theta plus cosine squared theta equals 1. We have 1 plus tan squared theta equals secant squared theta. We have 1 plus cotan squared theta equals cosecant squared theta. So hopefully as you get these committed to memory, then you won't have any trouble remembering what goes with what. The top one is the one that gets used the most, and so that everybody knows, so very easily. But what happens if you get on an assessment situation and you go, oh no, I can't remember? Because you're going to see sometimes tangent will be paired up with cotangent in the same identity, and sometimes it won't. So if I can't remember how to get this, I can derive it as long as I remember this and I remember my quotient identities. So how that works out, and I went ahead and worked both of them out, is this. So since tangent is sine over cosine, I start with that first basic identity, and then because in my quotient identity I'm dividing by cosine, I'm going to divide by cosine here. But remember, these are Pythagorean and they're powers, so that means what's on top is sine theta, So that means what I need to divide by is cosine theta, or cosine squared theta. And so in essence, right here in this fraction, I have sine theta on top, cosine theta on bottom. And so when I have sine over cosine, I get tangent. And when I have sine over cosine twice, I get 2 tangents. And so that leaves me with tan squared theta. Well, when I go to the next fraction, anything divided by itself is 1 except 0. So that's 1. And oh, look at that. We have a reciprocal identity. So if you remember from above, the reciprocal of 1 over cosine is secant. And now I have 2 of them because that's cosine squared theta. So this is the identity, and that's that Pythagorean identity right there. I can do the same thing to derive the last of the Pythagorean identities, but this time I remember that cotan of theta is cosine over sine, so I'm dividing everything by sine, and because it's in a Pythagorean situation, I'm dividing everything by sine squared theta. So anything divided by itself is 1. Cosine squared theta over sine squared theta is cotan theta twice, because I would have cosine, sine, so I'd have 2 of those fractions, so that's why I get cotan squared theta. And then another reciprocal identity twice, because 1 over sine theta is cosecant, but we have 2 of them with that power 2 right there, and so that leaves me with cosine squared theta. So this is not what I would really want you to be doing every time, but I know sometimes you get on assessment situations and you have a blank out moment, and if that's the case, now you have a quick way to derive these 2 as you go. Hopefully everything on this page is what we consider basic trig. In other words, basic trig identities, basic trig properties. And so just like you learned 2 plus 2 is 4, and that's a basic in the number system, these are basics in the trig system. And so hopefully the goal is we're going to do enough and we're to talk about them enough. We're going to say them, hear them, see them, do them, write them, use them, that these will be part of your muscle memory in your brain, and it won't be really sitting down and just memorizing stuff, that you're going to see these and work with these enough that it just becomes part of your working memory. We do have lots of identities that we will have to spend a little more time memorizing, which is not something I do often because I always try to show you ways to tie it and connect it to things you already know. But there are just some new things as we're hitting trig that you're just going to have to sit down and learn. So hopefully none of that will be the case here because we're going to use them and frequent these identities a lot. And so you'll just kind of get to where all of a sudden you're just going to go, oh, well, I know that. So that's kind of where we're at today. Now we're going to work through the problems that are in this section. And so when I'm working through these problems, I am looking at how they come together, and then I should have a triangle on every problem. The first thing you do is draw your triangle. Okay, if you don't have a triangle in your work, you will probably lose some points in grading because that's a must. It's not an option, it's not a suggestion, it is an absolute requirement. So there should just be triangles all over the place. It should be raining triangles on your page. All right, so here's the first one. We have a triangle 5, 12, 13, and we want to find all 6 trig ratios. So when I do this, I need to create a triangle for my 5, 12, 13, and notice it doesn't give me any information about the angles. But I do know from geometry that the side longest in a right triangle is always opposite the 90-degree angle, and that's the hypotenuse. So in this case, that's going to be 13. And then we can put in the 5 and the 12 in our triangle as we go. So here is my triangle. So the first thing is it's a right triangle, and you can see it's not drawn to scale, and actually I didn't even get very good at getting a perpendicular one, so I bet you can probably draw one better. I label where my theta is going to be, so it's down here, so that's my point of view. The side opposite would be that one, and so these two legs are going to be 5 and 12. You could say 12 and 5, but the 13 has to be on the hypotenuse. Then I'm going to set up my trig ratios so that they are paired with their reciprocal. So I'm going to do sine theta, cosine theta, tangent theta, and then opposite sine, I'm going to do cosecant, opposite cosine, I'm going to do secant, and opposite tangent, I'm going to do cotan. And the reason I'm going to do this is I'm going to use the fact that those are reciprocals, which means the fraction turns upside down. So as I work through this, I can fall back on my SOHCAHTOA, and if you need to write that at the top of your page because that helps you get the ratios right, then write it at the top of your page. If you can do it in your head, then that's fine too. So I'm doing sine, cosecant, cosine, secant, tangent, cotangent. So when I do sine, which is opposite over hypotenuse, so from this angle, opposite hypotenuse, that's where I get my 12/13. And because I know that the cosecant is its reciprocal, then I can turn that fraction upside down and I don't have to calculate it. I just know what the cosecant ratio is. So now I move over to cosine. So cosine is adjacent over hypotenuse. So the adjacent is over the hypotenuse, which makes that 5/13. And then I can flip that fraction upside down and I have my secant value of 13/5. Then I go to tangent, which is opposite over adjacent. So that's 12 over 3, 12 over 5. Okay, so I did fix that, so I have the right number there. Sorry about that. So I have 12 over 5, and then its reciprocal is 5 over 12. So you can see how quickly I can do all 6 if I line the original trig function up with its reciprocal. So now I'm going to look at problem 2, which says an isosceles right triangle, and I want to find the 6 trig ratios. So if I have an isosceles right triangle, I have a triangle that has a right angle in it that also has 2 equal sides, which are here and here. So we know that a triangle has 180 degrees, and if 90 degrees of them are used up right here with this angle, that leaves another 90 for these two together. And since this is an isosceles triangle, since this side is the same thing as this side, this angle has to be the same thing as this angle. So I can divide 90 degrees in half, that remaining degrees over here, and that makes this one 45 and this one 45. So you should have remembered from geometry that you have special right triangles, and the special right triangles for a 40, 40, 90 would be the ratio of the sides. Let me get my degree marks on there for you. It would be x root 2 or 1, 1, 1 root 2. So this is 1, 1, 1 root 2. And then I'm going to complete my 6 ratios from that. Now you do have to remember when there's radicals, this radical 2 here, we do need to take care of that in the bottom, and we're going to rewrite that so the radical is in the top. So sine of 45 degrees, so from here, I'm going to do sine is opposite over hypotenuse. So opposite over hypotenuse, which gives me this 1 over root 2. And to get rid of the root 2 on the bottom, I'm going to multiply the bottom and the top by root 2, which leaves me root 2 over 2. So then that means when I turn this upside down, I have a choice. Am I going to use this original ratio, or am I going to use this ratio right here? And I want to be smart about it and save myself some energy. So I'm going to go back to the original one, because when I turn this upside down, guess where the radical is? It's in the top. If I turn this one upside down, the radical is back in the bottom, and then I have to rationalize again. So that's just extra work on my part. So going to the original ratio here and getting my final answer. So look what happens at cosine of 45 degrees. Well, I get the same thing, so I know how that rationalizes. And I know that I'm going to flip this one upside down for the reciprocal, so I can save myself some energy for secant of 45 degrees. For tangent of 45 degrees, it is this and this divided, so I get 1s. And that leaves me with a 1, which also makes the cotan of 45 degrees an easy one to do as well. It's also 1. For problem 3, we have an equilateral triangle. And remember, equilateral triangles are all angles the same and all sides the same. With the sides 2 units, we want to find the trig ratios. So we're going to go in here, and here's my equilateral triangle. And all of the sides are 2, all of the angles are 60, and then I'm going to drop this down here because I'm doing right triangle trig, so I kind of have to have, guess what, a right triangle, and I'm going to make the right triangle there. Well, if this altitude splits this, it divides this bottom side equally, and so I get 1 and 1, and then I know that it also splits this angle evenly, so that's 30 degrees and 30 degrees. So you can see right over here I have a special right triangle. Okay, so we have more patterns for 30, 60, 90 triangles. And again, let me get my degree marks on here, guys. So 30, 60, 90. We know the pattern is x, x root 3, and 2x, and then 1 root 3 and 2. So 1 root 3 and 2. So again, we go through the 6 trig ratios, and we have not 6, actually, we just found these trig ratios. So I have sine of 60 is root 3 over 2. Cosine of 60, so I'm down here and doing cosine, is 1/2. Well, when I switch to the 30 degree, now I have to go up here and use this as my point of reference. So this becomes the opposite side. This becomes the adjacent side. That means sine of 30 degrees is 1/2, and cosine of 30 degrees is root 3 over 2. So I'm hoping when you look at these, you notice that there are some patterns there. The sine of 60 degrees happens to be the same ratio as a cosine of 30 degrees, or the cosine of 60 degrees happens to have the same ratio as a sine of 30 degrees. And that's because we're in the same triangle, and 30 and 60 are complementary angles. When they're complementary angles, then if I take the 60 degrees and use its complementary angle but find the cosine of it, I do get the same ratio. So if you're noticing the pattern, we have sine of 30 degrees equals 1/2, which is also the sine or the cosine of 60. So think about it this way. If they're complementary angles, I take 90 minus the 30 degrees and I get 60 degrees. And then I find the cosine of 60 degrees, which gives me the same thing here. If I had cosine and this was my angle, I could do 90 minus 60, which is 30, but then I would find the sine of 30 degrees. So we have some complementary or cofunction angle identities that we're going to look at. Now we're going to go into way more detail with this when we get into the full cofunction identity section where we're actually in radian measures, but since we haven't really talked about radian measures yet, I've got all of these listed in degrees so you can kind of work from there. So I have sine of 90 degrees minus theta is cosine of theta, tangent of 90 degrees minus theta is cotan theta, secant of 90 degrees minus theta is cosecant of theta. And so then the reverse can be true, right? We could do cotangent of 90 minus theta equals tan of theta. And so you can go back and forth. So those are the last one of some of the basic identities that we're talking about right now. For question 4, we are given information about a triangle. We're given the triangle here with a side 15, a side 8, and theta, but we were not giving this information. So before we can do all the trig ratios, we got to know the length of the hypotenuse. How do you find the length of the hypotenuse? Well, you use the Pythagorean theorem. So I have 15 squared plus 8 squared, and that would equal something squared. And so that something squared is going to come into play here when I'm trying to find that, and then I take the square root. So actually, I have 15 squared plus 8 squared, which is 289, and the square root of 289 is 17. So remember, when you're adding x squared plus a squared plus b squared equals c squared, this is c squared. So don't forget to take the square root of that, and this just happened to be a perfect square. So then I can go through my ratios. Again, write SOHCAHTOA if you need it, but I can do opposite over hypotenuse and then flip the ratio. I can do adjacent over hypotenuse and then flip the ratio. I can do tangent and go over to cotan and flip the ratio. So that takes care of that. There's another triangle on this section. So if you were in class, I don't think we actually did the second one, but it's here if you need another example. Again, we were given all of this information, but we were missing the length of the side. So then we did the Pythagorean theorem. And once we did the Pythagorean theorem, we knew that the length of that side was 8.5. And then we could go through and do all our ratios again. So sine is opposite over hypotenuse and flip the sign for cosecant. Cosine is adjacent over hypotenuse and flip the ratio for secant. Tangent is opposite over adjacent and flip the ratio for cotan. So if you did look at the triangles, you know that they are similar triangles. Corresponding sides are proportional. The ratios are the same. So I can see right here sine of theta is 8 over 17, which happens to be approximately 0.471. And over here in the other triangle, sine of theta was 4 over 8.5, and that was approximately, again, 0.471. So you'll be given information in various ways. So the last problem, they gave you a triangle with some missing information that you had to fill in. They could just give you a ratio like this one. They gave you cotan of theta equals 3 over 2, and it says find the other trig ratios. Again, first thing you do is lay out your triangle, so be sure you're marking your point of reference, which is my theta down here. So then when I do cotangent, I'm looking at adjacent over hypotenuse. So adjacent is here, hypotenuse is here, and that's when I'm laying out my triangles, right? Okay, so to find the missing side, then I do Pythagorean theorem. I don't care if you write this down because it's pretty easy, right? This is just 9 plus 4, and you take the square root of 13, and you get the length of that side. But I did go ahead and write it out in my notes just in case you were not sure about that. And so the other trig ratios would be sine, cosine, tangent, cosecant, and secant. I would start down here with tangent because if this is cotangent, when I flip the reciprocal, it's 2/3 and I have tangent done. Sine, again, is opposite over hypotenuse, radical in the bottom, rationalize it out. So I end up with 2 root 13 over 13. And so remember, smart flipping over here, right? So if I flip the original one, I get that radical up in the top. So that 1 is kind of right there on the check mark, but that is square root of 13 over 2. And then cosine is adjacent over hypotenuse, so that is 3 over root 13. Rationalize the denominator, you get 3 root 13 over 13. And so flipping the original ratio puts the radical in the top, and I get root 13 over 3 for secant of theta. And so those are the other trig ratios. In this case, you're given two ratios. So you're given secant of theta equals 5 and tangent of theta equals 2 root 6. So remember, those whole numbers can be turned into fractions by just putting a 1 underneath. 5 over 1 and 2 root 6 over 1. And we know that when you do that, then secant is hypotenuse over adjacent, and tangent is opposite over adjacent. So then I have 5 over 1, and I have 2 root 6 over 1. So I can use these two ratios to fill in my triangle. So remember your theta for your point of reference. And so hypotenuse is 5, adjacent is 1. And then tangent would be opposite over adjacent, and you can see those 1's line up in both of them. So now I have my triangle, and I'm asked to find these 4 things. So to find cosine of theta, that is adjacent over hypotenuse, so that's 1/5. To find cotan, remember that's going to be adjacent over opposite, so that's going to be 1 over 2 root 6. But careful, when you're rationalizing the denominator here, the radical 6 is all you need to get rid of. right? So you're multiplying the bottom and the top by root 6. Don't go ahead and multiply by 2 root 6, or that you're going to increase your number size, and then you have to simplify back later, so that's just a lot of extra work. So I get root 6 over 12. Now here is a complementary angle one, so this, remember the angle, cotangent of 9 minus theta is tangent and whatever theta is. So then I go to my triangle and I find this. I find tangent of theta in my triangle, which is opposite over adjacent. So I end up with 2 root 6 over 1, which is just 2 root 6. So you can kind of see how that identity played out right here. And finally sine, which is opposite over hypotenuse. So opposite over hypotenuse is 2 root 6 over 5. The radical's on top, so we don't have to do anything else with that. The last thing we're going to do, problem 7, is kind of introduce you to how you do a proof or you do simplifying. So don't panic when I say proof. Proofs in algebra are not the same thing as proofs in geometry. Excuse me. Proofs in geometry are 2-column proofs. You have a reason, a given, and then you have a reason. In simplifying or proving in algebra, okay, so to prove, we're going to have one equal sign per line. Our steps are going to move down the page. We are only going to work on one side of the equation. No algebra steps, so no add, subtract, multiply, divide, square, square root, anything like that. We are going to be able to replace something with an identity and simplify. And then we're going to do it the same way for simplifying and proving, just to keep it consistent, make it a little easier. But the difference is if you have to prove something, it will say show or prove, and you have to get everything committed to paper. Nothing can be in your head. It's got to be on paper demonstrating what's happening. If you're simplifying, you can do a little, you can like mark out some things and you can do a few shortcuts there. Okay. So it's going to give you directions, or sometimes you're just going to have to know. So it's going to say transform the left side of the equation to the right side or something like that. And so in this case, this is our problem we're going to do. It gives you cotan alpha sine alpha equals cosine alpha. And it gives you this restriction right here, which means that alpha is between 0 and pi over 2. So that means it's in this first quadrant of the circle. So we can go around and look at the pieces of the circle. This would be 0, 90 degrees, 180, 270. And then we know halfway around a circle is 180 degrees or pi. And halfway from 0 to pi would be pi over 2. So what it's saying is that it's going to be restricted in here. When we get into the point where we're solving equations, you can have multiple angles and answers to problems. And so usually when there's a restriction, it's restricting, down to the specifics. So now we could we're going to write down the left side and then an equal sign, and that's going to be considered our first step in our proof. So here we go. So it says prove left to right, so I write down the left side and then I put an equal sign, and so this is where I'm beginning from. Now I'm looking at this. I'm not looking at this side over here. This is where I'm going to end. So I know from the identities we looked at the beginning is I had a cotangent identity that I could write using sine and cosine, and I want to use that particular one because of this sign right here. So that's my quotient identity. So I took out cosine alpha and I took out cotangent alpha and I replaced it with cosine alpha sine alpha. And then I still have this sine alpha over 1 here. Well, in simplifying, just like we do other ways, we know if we have a numerator with a denominator that they can simplify, so I can mark it out. If you were doing a proof, then when we get into proofs in chapter 5 more, you would have to rewrite this, show that it's something divided by itself, and do some of those things that you can just kind of know when you're simplifying. So technically when I mark these out, what I have left is the cosine alpha from this side, and I have a 1 from this side, and we know 1 times anything is just that. So simplifying, I wanted you to see what's going on. This is the then simplify part. That if you went from here to here because you could see that this is going to happen in a simplification process, that's fine. So now look what we have. Remember, we started here and we proved to here. So we started here, that's this side. We proved to here, that's down on this side. Notice there is nothing in your proof on the left-hand side because we only work on one line at a time. We have one equal sign per line for each step of our simplification here, and that's the form that we'll use for both proof and solving. The nice thing about doing the form this way is then if it asks you to prove right to left, you don't have to change your form. You would simply write down the right side over here, put your equal sign, and then start transforming the right side until you had the left at the bottom. So I think it makes it really easy when you're following this process and pattern. So that's the notes for 4.3. I will do a separate video and go through the 4 application problems from 4.8, so you'll have that, and hopefully feeling pretty good about it. And once we get through these 2 things, our next step is we'll kind of jump back to the very beginning. It's just 4.1, and we'll start learning about some of the basic ins and outs. So we'll talk about really what radian measures are, what degree measures are, how to use the calculator for some things, and understand all of those basic ideas. Thanks, guys.